Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, well done for showing up on a Monday morning, fresh from partying. This is Andreas Lowe, who's from University of Utrecht. He's interviewing for a postdoc today. And please feel free to ask questions during his talk. Good idea to help him to take a temperature. And we'll be done in an hour.
Yep, thanks for the introduction. I'm going to talk about structural polymorphism in generic Haskell. I hope it will become clear what that is. The talk is structured. I'll give a very little bit of motivation, or it's more positioning the kind of research I'm going to talk about, what area it's in. Then the whole next part is genericity and other types of polymorphism is also motivation. I'm going to try to explain why genericity in the sense of generic Haskell is something you really want. I'll give a few examples of applications and generic functions, and in the end I'm going to talk a bit about generic Haskell as an implementation, or what the compiler is doing, what we've done in the project, and that will be the conclusions. So first I'll start with the motivation part. There's certainly many aspects about programming languages that you can strive for, but I hope that most of you will agree that these two I've named here are among the important ones. So one thing that programming languages should be for is abstraction, and one thing that's nice to have in programming is static guarantees, and I'll go into a little bit more detail. Abstraction is a very general concept which is at the core of computer science as a whole, I think, but in programming languages you find many different concepts of abstraction, and over the years you got more and more. So there is loops, modules, functions, classes. In functional programming languages you have higher order functions, and it's easy to see what kind of advantages you have. You get to reuse your code, you can prove consistencies of your program better, you can test better, you can write down things in a much shorter and easier to understand way, and things like that. Static guarantees, on the other hand, well, they allow you to prove properties about your program, and it's nice if they are supported by the programming language. So almost any programming language checks the program for syntactical correctness, and there are also many notions of scoping rules, or most compilers will report if you're using an identifier that's unbound. But there is also the notion of static typing, and that's not so common. Now, many programming languages have that, but that means that there are checks at compile time that you're using the values in the way you should use them, and that you're not adding things together that don't make sense. And the advantages of static guarantees are possibly efficiency, most of all safety probably, that you just know at compile time that a certain class of errors is not in your program, and that will hopefully lead to a higher quality of the resulting product. And it will make it easier, probably, not eliminate the need for testing, but it will make it easier to test certain things. So the unfortunate thing is that both these goals I've mentioned, abstraction and static typing, or static guarantees, that they are somewhat mutually exclusive. The reason is that it's certainly impossible to analyze all interesting properties of a program at compile time, because most of the interesting stuff can be reduced to the halting problem. That means if you're designing a safe type system for a programming language, it necessarily is conservative. That means either it rejects programs that actually would work, or, well, in other words, it prevents you to write programs that you want to write, because, yeah, well, I know, for example, that a certain program works and I get a type error, but I can show that this if I could give a more specific type, then it would still work. But if I would increase the power of the type system, then it might no longer be decidable. In dynamically typed languages, all these problems don't occur because you don't check statically, but at runtime, but that's at the loss of safety. So that means you don't check at compile time at all. You'll be able to write all running programs, but you won't know you've run into an error before you've actually seen it at runtime. So the whole research of generic Haskell can be seen in this area, that we want to increase the power of the type system without losing decidability, and we want more abstraction but maintain safety. So that's the whole setting. Now let's look at what I understand with genericity and generic Haskell. I'm going to give a very brief introduction into Haskell. I don't know how many people are familiar, but I just want to make sure that you more or less understand the notation. I'm going to show some code, and I want to make sure that you understand the notation I'm going to use. So Haskell is a statically typed pure functional language with lazy evaluation. That it's pure functional and that it has lazy evaluation is not really relevant to this talk. So mostly it is a statically typed language. And functions are defined by pattern matching. So if I define a factorial function, I can give two cases, one that matches only if the argument is 0, and then I return 1, and one that matches for all other things, and then it returns n times factorial of n minus 1. And every function has a type. That's also important. And usually the types can be inferred by the compiler, so the programmer doesn't have to write them down. But factorial function has the type int to int, and if you would want to write it down in Haskell, you'd write it like this. And functions with multiple arguments are written in carried style, which means basically that a function doesn't take, well, you can make a function like AND, which is logical, and doesn't take two Boolean values in a tuple, but it rather takes a bool and then it returns a function from bool to bool, so two bools after each other, which allows partial parametrization. And AND on true and true returns true, and AND on anything else returns false. Okay. Then Haskell allows you to define your own data types, which is very, very nice. And new data types can be defined by means of this data construct. And here I'm defining the type of natural numbers, and it has two so-called constructors. Either it is a 0 or it is a successor of another natural number. So this is a tagged union, if you want to, where you say it either is a 0 or it is a successor. And then you can combine these constructors to form values of the type. So this suck of 0 would represent the natural number 3 in this data type. And then functions are often defined recursively by induction on the structure of a data type. So the addition on these natural numbers can be defined by pattern matching on the different constructors for the second argument. Plus m of 0 is just m, and plus m of the successor of some other number is the successor of the addition. The data construct in Haskell is extremely flexible, and I'm just going to show a few examples. There are many more things that you can do with it. First of all, you can define ordinary union types that just have a limited number of different values. There is this rather useless type time info, which you could imagine as going together with a time value and telling you how to read it. So either it's a 12-hour system and it could say it's an AM time, or it's a PM time, or it's a 24-hour system and then it could say H24. So this data type has the three values AM, PM, and H24 and no other values. It can be used to define something like record types, just grouping different things. So you can have a software product, a package, and it could have a name which is a string. It could be belong or be produced by a specific company, which could be a huge data type containing all sorts of information. And it can have a version and maybe a date when it was released. You can parametrize data types in Haskell, which means this data type maybe takes an argument, which is also a data type, this alpha, and the maybe adds an exceptional value to an already existing data type, which means either it's nothing, which is this exceptional value, and then otherwise it's just an alpha. So you can use that to add this nothing to any data type. And then there are lists in Haskell, one of the most important data types. They have a slightly nicer syntax because they occur so often. You write this a list of alpha. It's either the empty list, it's written like this, or it is the head element of a list followed by another list. And then the last data type I'm going to show is trees, binary trees with labels at the leaves. It either has a leaf of the parameter data type, or it's a binary node of two trees. And there are more data types. Of course, there are more, but there are also, I've shown that data types can have recursion, and I've shown that they can be parametrized, but they can have multiple parameters. They can be parametrized by type constructors. So this tree is a type constructor because it's a parametrized data type. So you can also have parametrized data types as arguments if you want to. You can have nested data types and things like that, but I'm not going into that in this talk. Although the data construct is so flexible, it still is the case that all data types I've defined follow a common structure. They are parameterized over a number of arguments, possibly 0, and each data type has several constructors or alternatives. And then per constructor, there are multiple fields, and then there is possibly recursion, like in the list data type or in the tree data type. So Haskell has a relatively interesting feature that it allows parametric polymorphism. That means it allows you to define functions that work on all data types in a uniform way. You can, for example, define the identity like this, the identity of x equals x, and then it gets the type for all alpha to alpha, which means you can apply it to anything. You can apply it to a list, a tree, a list of lists, an integer, whatever you think of. And you just write it down and it gets this type. You don't have to write instances for different types. You also can swap the elements of a tuple, of a pair, x, y, is assigned to yx, and then it gets this type for all alpha and beta, alpha, comma, beta, arrow, beta, comma, alpha, which means take two possibly different things and swap them around. And you can take the head of an arbitrary list, which returns the head element, provided it's non-empty. So we can write these functions and they work on all data types in the same way. And let's look at the equality function as an example now. It's easy to define a notion of equality in your head. You have an intuitive algorithm when two values of a specific data type are equal. If you think about it in the way Haskell data types are defined, they all have different constructors, but certainly if two values are to be equal, they should both belong to the same constructor. So they must belong to the same alternative. And then if they belong to the same constructor, well, each of the constructors has a number of fields or arguments, and then each of the fields of the one value must certainly be equal to the corresponding field of the other value. So this is a somewhat recursive definition, but at least this is certainly the idea of equality. And it's easy to define equality for data types in Haskell. If you're given the data type time info, for example, which had these three values, AM, PM, and H24, you can define equality as follows. Well, both values must belong to the same alternative. So if you have AM compared to AM, it's true, and PM compared to PM, it's true, and similar for H24. And if we have any other combination, then it's false. So that's what I mean with both values must belong to the same alternative. And if we have a record-like type like the package, where we group different values, well, it's easy. Then always two values belong to the same constructor, and then we have 4 arguments here and 4 arguments here, and the corresponding fields must always be equal. But this requires that we have equality function for the respective data types, string and company, version and date. Otherwise, we cannot define the equality function for package. But if we have, then we can easily extend these equality functions to the new data type. It's also possible to define equality for parametrized data types. If we have maybe alpha, which was either this exceptional value nothing or a just of alpha, well, then we can define an equality function for maybe, which compares two maybe alphas and results in a bool. And again, the same pattern, both values must belong to the same alternative. So they either must both be nothing or they must both be just. And if they're any other combination, it's certainly false. If they're both nothing, then the result is true, because nothing is equal to nothing. If they're both just, well, then we have to compare x and x prime with some equality function, but we don't know the type to put here, because that's alpha, and it could be any alpha. The best way to solve this problem is to just abstract from that type and take an equality function for alpha as an argument. So we add another argument here, we get this equality function for the element or for the alpha as the first argument, and then we use it over here. So about the lesson we learn is we can define equality for parametrized data types, but then we require to know the equality function for the arguments of that data type. And, well, we see that the equality function depends on itself because I just call it depends on itself because it uses itself on the right-hand side. So now we've seen a lot of things about parametrically polymorphic functions, and we've analyzed how to define the equality function. So we can ask, if we can define equality for any data type, which is what we have done, or we have given example data types and came up with an equality function, wouldn't it just be possible to define a parametrically polymorphic equality function? And that's unfortunately impossible. We cannot define a function of this type, alpha to bool, which is the equality of x and y in the intuitive sense. And that's a consequence of the parametricity theorem, which is, I think, originally due to Reynolds, but has been also made public or much more popular by Wadler later on. And that is a more general theorem which allows you to derive results from the type of a function. And it basically tells you that if you get two alphas, you don't know anything about them. They're just boxes, and they always look the same. So if you're going to write a deterministic function on two of these boxes, then you either always can say true, or you can always say false. So the only functions you can write here are the constant function true or the constant function false. But you cannot look inside of the alpha, and you really need to look into the structure of the types. So that's not good enough. So that's what we've seen so far. We can define specific equality function for many data types. According to this intuitive algorithm we have, both values must belong to the same alternative and the corresponding fields are equal. we cannot define a parametrically polymorphic equality function because that's just not expressive enough. Well, Haskell has a different functionality, luckily for us. It allows us to place different functions that work on different types into a type class, and then we can use the same name for a function which works differently on different data types. So we can use one name, namely this symbol for equality, for all our different equality functions. And that looks like this. In Haskell, you can define a class EQ of A, where we have the equality function, which takes two alphas and returns a bool. And then a class is somewhat like a set, or you could say a unary relation on the data types. And you can make a type a member or an instance of the class by defining the class operations. In the case of equality, we have one operation, which is this equality function. And we can make the types we've seen so far, time info and package, instances of the class by assigning the general name to this specific, where time info and package, you should see this as a part of the function name here, by assigning the specific equality to the general name. And we can also do this for maybe or for lists, but then we need the equality function for the element type, because the parametrized equality took an additional argument. And this dependency on the class level becomes an instance constraint. It's not really important that you understand that. It's only important that you know that this is possible to do in Haskell. And then you can use the same name, namely this equality symbol, for all these data types. Okay, and then now you have sort of implicit type names where you had explicit indices earlier on. So, well, is this satisfactory? Well, what can we do now? We can define an overloaded version of equality, but we still have to write all the instances ourselves. And although we have an intuitive algorithm to define equality for all data types, whenever we have a new data type, we have to define a new instance. And this is work, and it bears the risk that we do something wrong, and it might even be a lot of work if the data type is large. So let us define the equality function once and for all. That's what generic Haskell or structural polymorphism is about. Structural polymorphism, which is called generic programming in the functional programming community, makes the structure of data types available for the definition of type-indexed functions. What this means in real words is that you can define functions which are, well, inductively on the structure of all data types. Something like equality. And in context, that means, well, we have the parametrically polymorphic functions, which are a relatively small class, and we have the ad-hoc polymorphic functions, which are defined by overloading, and they are a much larger class. Of course, you can make every parametric polymorphic function into an ad-hoc overloaded function by just giving the same definition for all data types, defining instances over instances. And the generic functions, or the structural polymorphic functions, give you a new layer in the middle. They are not parametrically polymorphic because they inspect the structure, but they also don't do arbitrary things for all data type, and you don't have to give definitions for every data type, but you rather can describe the behavior for all data types with a few cases. We're now going to look at examples of generic functions. Well then, let's define a generic equality function. We now define equality again, and in addition it gets a type argument, which I make explicit here by having these angle brackets. and then it has the type alpha to bool. Now I'm defining it for a few data types. I mean, the data type unit is a very simple data type. It has just one value, which is also called unit. And if I have just one value in a data type, it's trivial to define equality for it. If I get twice the unit, I just return true. And the next data type I'm going to define this generic equality for is the sum data type, which is the alternative of two things. It's either an in left, this is pronounced, of alpha, or an in right of beta. And of course, both values must belong to the same alternative. That is reflected here again. If they both belong to the in left alternative, then the x must be equal to the x prime according to the equality function for the alpha. If they both belong to the right alternative, then the y must be equal to the y prime according to the equality function for the beta. And if they belong to any other combination of alternatives, then we return false. And then there is a third type, the product of two values, which I use an infix constructor here, but it's just a combination of alpha and beta. And if I get a combination of x and y and a combination of x prime and y prime, the corresponding fields must be equal. So x must be equal to x prime according to equality for alpha, and y must be equal to y prime according to the equality for beta. Well, and then I might add a few cases for built-in data types. Integer and character are data types in the language which are machine implemented in a way, and they directly correspond to data types which have primitive functionality. They cannot easily be expressed in terms of other data types. So we might want to add cases for those and give specific built-in definitions for equality on those two or whatever. But if we have this, and this is what Generic Haskell allows you to write down. If we have this, then we have one definition, and we can use it on all data types. So this is all you ever have to write. That's the difference with type classes. With type classes, if you have a new data type, you have to define a new instance. If you've written down this for unit, sum, and product, and maybe a few primitive types, then you have a complete definition which you can use on all Haskell data types. So a function that is defined for the unit, sum, and product types is called generic or structurally polymorphic. And it works automatically for all data types that do not contain primitive types like integer or character, but if you add cases for integer or character, then it works for those as well. And if you call it on a data type where it's not explicitly defined for, then that data type is internally, implicitly deconstructed into a representation that involves these types, unit, sum, and product. And that's how it works. And as I've already said, unit is to represent a constructor with no fields, such as nothing or the empty list. That's what unit is used for. And the sum represents a choice between two alternatives or two constructors, just captures that pattern. And the product represents the sequence of two fields, of two arguments to a constructor. And I'm just going to show one example. If you have the parametrized type tree, which is either a leaf of an alpha or a binary node of two trees, where you can view this as a sum of two things because it has two alternatives, as either a sum of an alpha, because the left-hand side is just a single field, alpha, or the right-hand side has two fields, so we're using the product here, a product of two trees. And this is in a way a recursive view, but by applying it over and over again, we can see how we can derive from the generic equality function an inequality function for trees. And that's what generic Haskell does. So with the definition of equality, we can now use this function on data types like time info or tree and evaluate things like that. And I'm going to show you this quickly, just that you believe me that I'm not talking about stuff that doesn't really exist. That this is really something you can do in generic Haskell. So this is the equality function. As you've seen it, this is how it looks like in a generic Haskell module called demo.ghs. And it has a case for unit, it has the cases for sum, it has the cases for product, and it has the cases for integer and character. It's exactly what you've seen before. And these are the two data type definitions of time info and tree. And we're going to run 3 tests. The equality of time info on AM and H24. So the first test should be false. The equality of time info on PM and PM, the second test should be true. And the equality on a tree of integers, and there are 2 trees here, and they are slightly different because the one has a 2 and a 4, and the other one has a 4 and a 2. So this should be false again. Now what I'm going to do is I'm going to run the generic Haskell compiler on demo.ghs. This is rather unspectacular. It just doesn't say any. I could use the -v flag to let it say a little bit more. And it writes a file demo.hs. So generic Haskell, I'm going to tell a little bit more about the implementation in a few minutes, but it compiles a generic Haskell file into a Haskell file. And this Haskell file I can run with GHCI. This GHCI just sets a few additional paths so that it will find the correct library. Oh, I should run it on demo.hs, of course. And then I can run test 1. You see, test 1 returns false, as it should. Test 2 returns true, and test 3 returns false. So that's what you see here. False, true, false. These are exactly the same examples. Okay, now I've talked about equality for a long time, and equality isn't really an interesting function, but it serves as a nice and simple example to argue why you need something like generic functions. There are many application areas of generic functions, and I'm going to give you a few examples of other functions that can be written as generic functions. So the whole area of comparison is an important application area. Of course, you can not only define equality, but you can also define orderings on data types using generic functions. Then there is a huge application area in parsing and printing, so you can use it to read and write data type values into a canonical representation that is human readable or something. You can use it to read and write into a binary representation for storage on disk, for transfer to other programs. You can, for example, read and write XML documents to a typed Haskell value, and then do type save operations that modify the XML value and write them back into another XML value as generic function. And you can use generic functions for things like compression or even encryption. And then you can use generic functions to generate values. For example, you can have a generic function which is very simple that generates a default value for each data type. You can imagine if you have an interactive editor and you're having a widget where you want to put in a default value always according to the type of value that's expected. You can use a generic function to derive such a value. You can enumerate all values of a data type, And what's also very interesting, you can possibly randomly generate test data using such an enumeration function that's used in a Haskell tool called QuickCheck. Well, it's not actually using generic Haskell, but it's using generic programming techniques to do that. And you can, this is also a very important area, you can use generic functions to define traversals on large data structures. If you have any large data structure representing a company, representing a tree of dependencies between certain abstract issues, if you have an abstract syntax tree of a programming language, or things like that, you always have operations to do that traverse the whole tree and do interesting stuff only in little places. Like you have to collect all 3 variables from a large abstract syntax tree. That only affects a very few places, namely the place where the variable is stored, where you add something, and then the location of binders where you remove something. And all the rest, you are doing generic behavior. And if you write these things as generic functions, then you save a lot of work. Was a question? Okay.
So you can do these things up to the extent that you have metadata definition to help you be able to guide the process to do this. And yet the whole point of Haskell is that the actual data type declarations have almost incredibly succinct. Programs usually make it take advantage. But the whole point of your data type declarations will say nothing. No metadata or those metadata. Apart from, competency stuff. Now, I don't see, there seems to be a need metadata to do this stuff in reality. You can't just choose an arbitrary XML format based on you can't put a quality function the actual order that you want to do things. Metadata to guide each of these.
Yes.
So I don't see how anything sets it apart copes with that problem. I mean, it's just not set up right to be able to really generate.
Okay, so if I understand the question correctly, it is that this all works well, but it requires the data types to contain metadata, and metadata is something you don't want to have in your Haskell data types. And you named XML as an example, and that's actually true. That there is very extreme. If you choose a representation as a Haskell data type canonically for an XML schema or something like that, you get a very horrible data type to express all the sorts of constraints, and you obviously don't want to work with that data type anymore. And we've actually encountered that problem. There are 2 answers to that. First of all, if you're working with generic functions, then it becomes easy even to handle such horrible data types. Because if you're writing generic functions, then you don't worry about the actual layout of your data type anymore. And if you're willing to commit to work only with generic functions, then you can work on data types which are much more complex than what you usually would want to work with. That's one answer. The other answer is specifically for XML, Frank Atanasov has written a tool which allows you to, also using generic functions, to design a data type which you would like, which has little metadata for an XML document, and convert this automatically derived data type into the simple data type using a generic function. So it automatically applies canonical isomorphisms to simplify the data type. But you're definitely right. There are certain tensions here, and this is probably a good area for future research to do more in this direction to automatically simplify things, or maybe have a mechanism to specify metadata outside of the data type declaration to guide this process. Does it partially answer your question at least? Okay. So want to quickly show the advantages of generic functions. Well, first of all, it's reusable. That's the most obvious of things. You can write a generic function, use it for all data types. I don't think I have to say a lot about that. Then it's type safe. This is in contrast to other approaches which allow similar things also in other programming languages. For example, C++ has this very powerful template language where you can also, I'm sure you can encode things like this in a very ingenious way. But if you have templates in C++, or if you have templates in Generic Haskell, which also exists, then the generated code is type checked. Whereas here, the generic function is type checked. If your generic function is type checked, then you know it will work on all data types. It will not produce a type error because you instantiate it to some new data type. That's a huge advantage. Then it can be very simple. These data types, you have to define it for unit, product, and sum. They are really very simple data types, and it's easy to come up with definitions for these 3 data types for most functions. Sometimes, if you have very complex data types, as Haskell allows you to write, it can be a pain to write even a single instance of a function for such a complex data type. If you want to come up with the equality function for only one data type, which is huge, or if you want to come up with a ordering function for one data type which is huge, then it can be lots of lines to write. So it can actually be easier to come up with a generic definition than to write one single instance. And this, I think, is also very important. Generic functions make your code adaptable. If you write, as I mentioned, there is an example where you can use generic functions to operate on large data structures, on XML documents, or on abstract syntax trees to perform operations like collecting free variables or modifying, renaming certain parts of your structure. If you write these functions that operate in a generic way, then if you change your data structure later on, because your program evolves, you need a new alternative in your data type, you extend your language for which the abstract syntax tree is there, or the companies get a new hierarchical level, so you need to change the data type for the companies. Well, you don't need to change most of your functions then, if they are written in a generic way, because they are not tied to the layout of one specific data type anymore. They are tied to the generic layout of all data types, and only if really the logic of your program changes, you need to change or adapt your functions, but otherwise they'll adapt automatically. So the last minutes or final minutes of my talk, I want to say something about the Generic Haskell project. Generic Haskell has been a research project funded by the Dutch Research Organization from October 2000 to October 2004. Now I've been a PhD student there. The goal was to create a language extension for Haskell that supports generic programming. And when the project started, there already was quite significant amount of work and ideas available by Johan Jöring and by Ralf Hinze, which we used as a starting point. And obviously the project is now finished, but in Utrecht there will still be work on Generic Haskell in the future. The main results of the project are, I think, that compared to the original ideas are still present, but they were awkward to use in some places, they were difficult to explain, and there were yet some things that we couldn't express, and I think we've managed to simplify the whole theory a lot, to make it much easier to teach, to explain, and we didn't do this at the cost of expressivity, but we actually added additional things. So I think it was a successful project, and I think my PhD thesis is actually a reasonably complete documentation of the results of the project. I also have it with me, and it's available online if you're interested. The Generic Haskell compiler, which you've seen in action before, is a preprocessor. So extends Haskell with constructs to define type-indexed functions, what we've seen, and also type-indexed data types. I have a slide on that. And it compiles all these things to Haskell. So it compiles data types into isomorphic structural representations of the data types using these unit, sum, and product data types. And it compiles generic functions by specialization. So it actually produces specific instances for the types, the things you ordinarily have to write by hand. And it compiles then calls to generic functions into calls to the specializations. It has a couple of additional features, which I've been working on mostly, that allow you to easily define new generic functions from already existing generic functions. For example, if you have a generic function and you want to change its behavior only slightly, you can use a construct that I call local redefinition to, within a limited scope, redefine the behavior on a specific data type. You can use generic abstraction, which allows you to just define one generic function as an expression in terms of other generic functions without fixing the type argument. So the resulting function will again be generic and depend on a type argument. And you can extend in an almost object-oriented way. You can extend generic functions. So you can take an equality function and add a new special case, for example, for a specific data type to give a specific behavior on that data type. This feature is called default cases. And there are dependencies. I'm going to skip that, I think. I'd rather talk a bit or a few moments about type-indexed data types. It's also something that the compiler supports. That's generic functions one level higher. Generic functions are functions defined on the structure of data types, whereas type-indexed data types, this terminology is for historical reasons that they are not called generic data types, which would actually maybe be better, or maybe it would be better to call these type-indexed functions, are data types defined on the structure of data types. So I'm going to just appeal or give a few examples. Type-indexed tries are finite maps where you employ the structure of the key type to better store the values. So for example, if you have a key type which is an alternative of two things, you can store the values by just having two finite maps, one for the one alternative and one for the other alternative. And if you have a key type which is a combination of two things, you can store the values by having a nested finite map. So you first look up the first component, and then you get, as a result, another finite map in which you can look up the second component, and then you're at the value. So these type-indexed tries you can actually program in generic Haskell. And the zipper, so-called, is a data structure that facilitates editing operations on a data type, which if you have a data type, you can generate another data type from that, which allows you to navigate around the original data type and move a focus down and left and right and up and change values at specific notions. And this zipper data structure can be programmed in generic Haskell as well. There is an implementation which you have seen. In the current release, unfortunately, there are not all features implemented, or actually most of the features are implemented, but they have a different syntax, which is not compatible with the one used in the newest papers or in my thesis. But I'm currently busy to work on that, and I'm planning to release this version, which contains everything, in January. And type checking is unfortunately partially left to a Haskell, which doesn't say anything at all except that the error messages can be quite bad from time to time. So it's still completely type safe. If the Haskell compiler type checks it, it's okay, but you sometimes get type errors in the generated code rather than in the original code, which isn't really what you want. there's a huge amount of related work. I just want to mention a few things. I won't really have time to go into all the differences, but there is also a project on Haskell which is quite successful, which is based on the Scrap Your Boilerplate people by Ralph Lemmel and Simon Peaton-Jones. They are basically or originally focusing on this traversal idea that you want to define operations on large data structures. You're basically doing the same everywhere. You're only doing specific things in very few locations, and they have a very simple mechanism to do this. There is a pattern calculus by J and the Fish language, which is another specifically designed programming language for generic programming, which in my opinion, unfortunately, is very complicated to use. There is a huge amount of work on generic programming and dependently typed programming, because dependently typed programming is allowing you to have much more involved data types, and it encourages you to define many more data types than you would do in a normal programming language. That leads to the fact that well, if you, for example, can express things like a sorted list or a list with at most 5 elements, all as separate data types, to make your program more type safe, but it also means that you have to define functions like get the first element of that list separately for all these data types. And if you have more different data types in your language, you absolutely want something like generic programming to facilitate this. There is intentional type analysis, which is generic programming or has generic programming abilities, but more on a lower level, not for the end user. There is GADT's, generalized algebraic data types, which is in the direction of dependently typed programming, but within Haskell. There's template Haskell, which is templates for Haskell, but type checked only after generation, not prior to generation. Templates in C++, which is the same thing. There is generics in C# and Java, which is in a way a different thing, but I think maybe possibly it would be possible to do things like we do in Generic Haskell and these languages as well. And there is lots more I cannot mention. I want to conclude with future work. I want to work on, well, not necessarily only but things that are left to do are generic views. That's something we are busy with in Utrecht at the moment. We have seen this representation of data types into unit, sum, and product. Would be nice to have the ability of choosing different representations in some cases. Sometimes you want to have explicit fixed points, for example, to do more with recursion or stuff like that. And we've already have a prototype that allows you to choose different views, and the next step would actually be to being able to program different representations. And then type inference for generic functions, also busy with that at the moment. At the moment for generic functions you have to give the type signature, but it would be nice if it could be inferred. And we think that's possible in very many cases. And then, which I'm particularly interested in, is what I've already said. In the presence of a richer data type language, I think generic programming becomes actually even more important because you have more data types. So it would be nice to extend these ideas to these richer data type languages. Okay, that's it.
Any questions?
Type languages and type languages.
Mm-hmm.
So in what particular ways do you think that helps the sort of type languages sort of compete with?
It's a difficult question because Well, I talk a lot to people who are very fascinated by dynamically typed languages, and I often have the impression that they are choosing dynamically typed languages not actually for any rational reason, but rather for some sake of philosophical argument. But if one would want to argue for it, I think in general one of the least sold features of the Haskell language, I think, or even languages like OCaml, is that actually people should be realizing that type inference in most cases means that you don't have any additional burden by using typed languages. And I think there are two things, as I said. You cannot write every program you want in the typed languages because some things get rejected. And the other thing is you get as a benefit these guarantees. I think you can of course argue that generic Haskell allows you to write more programs, and since we are working on type inference, it does so without any additional cost, so you can actually get more things without working very hard. So that's a selling point. But in your particular case, I would say that if I look at programs typically written in languages like Python or Perl, then they could as well be written in a statically typed language already. They are not using the features of dynamic typing that much.
Those languages are often tolerant of sort of changes in schema.
Yes, but I've seen projects where they actually have coding standards not to do these things, or so that's sometimes if they tend to overuse these features, then my impression is they're getting confused by it, and then they sit down and then they decide not to use these features, but they still complain about statically typed languages because they wouldn't allow you to do these things. So
that's an advantage of generic Haskell is exactly that it's robust to data type.
Yes.
Like.
Yes. Yeah.
I like the type class facility because it enables you to define types with equality, which is an equivalence over data structures.
Yes.
Can you mix the two? Supposing I wish to, for example, have an ordering over arbitrary data types, but on integers I want this ordering to be divisible by.
Yes.
Can I sort of
Yes.
override?
You can. Actually, I've not gone into detail on this, but if you have a generic function, you're not limited to a specific set of data types. You can give this unit some product case, but you can give specific cases as many as you want. And then for the types which you have specifically defined, your specific behavior takes place, and only for the ones where you haven't defined anything, the generic behavior takes place.
It's really just a default convention.
It's just a default convention that you can fall back to a generic behavior, and it's even easier to do these things because you can use the generic equality function in your example and then have this default case mechanism, and you can just take the library function for generic program for the generic equality, add one additional case, and then you have a variant which defines the equivalence.
It's a very powerful facility, that.
Yeah, I like it.
A good note to finish on.